Hamiltonian mechanics is a more abstract theory of classical mechanics. It is based on the definition of a function that describes the energy of the system, called the Hamiltonian. Let's consider the Hamiltonian of the pendulum that we derived earlier, and further consider the time derivative. This time derivative gives a prefactor ml squared times 1/2 times 2 times the time derivative of the angle times the second derivative in time of the angle plus g divided by L times sine of the angle times the time derivative of the angle. And this should be equal to the time derivative of the energy, which actually is 0 if we assume that we have conservation of energy. Now we divide out prefactors. We obtain the second order differential equation, theta double dot minus omega squared sine theta is equal to 0, in which omega squared is the square frequency of the pendulum motion given by the ratio of g divided by L. Now we even can further simplify the equation, just letting theta be small, which means the sine just turns into the angle itself, leading to the differential equation that the second time derivative of the angle plus omega squared of the angle times the angle itself is equal to 0, which is nothing else like the harmonic oscillator that you discussed in classical mechanics. So this is just a glimpse of what you could do with the harmonic oscillator in classical mechanics, and you will hear about this in your further study. The Hamiltonian also plays a significant role in quantum mechanics. Now in quantum mechanics, a system is described by wave function psi, which lives in phase space P and Q. The wave function will be the eigenvector of the Hamiltonian equation, leading to an eigenvalue E, which describes the system. Hence, quantum mechanics is a very easy way to understand and count the number of states that a system can be in. Those eigenvalues are quantized, hence there's an easy graphical way to describe a system by just drawing as a function of the energy different energy states and eigenvalues of the system in question. Now, this model we will use throughout the lecture, but what you should keep in mind is that every eigenvalue describes an eigenfunction, although we only talk about the eigenvalues further.